Hello everyone and welcome to today's webinar. Today's webinar is titled Simulation-Driven Conceptual Design of Exoskeletons. My name is Christopher Iversen and I work here at Anybody Technology. Today I will be the host of this webinar and I will be joined by my colleague Bjørn Keller Ingelund, who is one of our research and development engineers here at Anybody Technology. Bjørn will join us during the Q&A session and help us out with answering your questions. In today's webcast, we have an external speaker who is Professor John Rasmussen, and Professor Rasmussen is heading the biomechanics research group at the Department of Materials and Production at Aalborg University here in Denmark. In today's webcast, he will share insights in his approach to simulation-driven conceptual design of exoskeletons. And the presentation will start in a few minutes or so. But just before we start, I will give you a general introduction and overview of the Anybody modeling system for those of you who is unfamiliar with the software or musculoskeletal modeling and simulations in general. First of all, I would like to point your attention to the control panel, which appears on the right side of your screen. You are very welcome to submit questions and comments via the questions panel during the presentation, and we will try to address the questions in the very end of this webinar. In case we do not get to answer all of your questions, we will try to do so by email within a reasonable time. So let's begin with having a look at what the Anybody modeling system actually is. The Anybody modeling system is a software that allows you to do musculoskeletal modeling and simulations. As input, it takes motion data as kinematics and forces, and it calculates the internal body loads as joint moments, joint reaction forces, and muscle forces. And here in the bottom of the screen, you can see a screenshot from the actual software. This can give you an idea of how the system actually looks. Today, Anybody is used in a wide variety of areas and applications. And a few examples of this is movement analysis, product optimization design, the field of sports optimization, orthopedics and rehabilitation, and assistive devices as exoskeletons. And the typical workflow in Anybody could look something like this. So you provide the recorded motion data as input, and then you can use the body models which you or others have built. You can then provide some kind of environment, which could be a special type of equipment or, for example, an exoskeleton. You can then use Anybody to combine these things and solve the muscle recruitment and run the inverse dynamic simulations. This basically means that we go from motion to calculate the internal body loads and the interaction with the environment in some cases. This gives us a simulation that looks something like this. We can then go ahead and output the results and use it for some kind of post-processing, which for example could be a finite element tool. But many users also closes this loop completely by doing some kind of design optimization and then run this cycle multiple times. And this actually brings me to the end of the introduction, and I will hand over the word and presenter role to John instead.
Thanks, Christopher. Thank you for the opportunity to speak to you today. I will talk about simulation-based conceptual exoskeleton design. And we're going to look into designing an exoskeleton for the work task that you see on this slide right in front of you, which is lifting a box and taking a couple of steps and then placing the box on a high shelf. So without any further ado, let's go on to the next slide, which is part 1 out of 3. So initially, let's try to set the scene for what we want to do with the design. And the first thing I want to do is to tell you what we will not do. So we will not be doing detailed exoskeleton design. And to explain what detailed exoskeleton design is, you can look at this picture. You can see here a suit exoskeleton, which is of course a product that you can buy and which is already designed in all details. You can add an exoskeleton like that to the body and you can investigate its effects. But that's not what we're going to do today. We're going to start from the beginning, from scratch, and try to do conceptual design of exoskeletons instead. So maybe some of you have taken design classes at university or maybe even in high school, and maybe you are familiar with the concept of a product life cycle. So if you imagine the graph that you see here, where we have time on the first axis and we have costs on the second axis. And then the idea is that over the design cycle of this of any product, we will go through some stages that are typical. So we will first realize that there is a need for the product, and we will develop some ideas and some concepts. Then we will start adding details. Perhaps along the way we need to take out patents or apply for patents. We need to build prototypes to check that it works out. Maybe we have to go through some certification procedures that can be more or less elaborate depending on what market we are targeting. And then finally, of course, we go to production and distribution. And if you look at which parts of this process are actually expensive, then you can see that the beginning of the process, where you just have a bunch of engineers talking to each other and throwing ideas around, is not actually very expensive. Whereas things start to get really costly at the point where you begin thinking about production, and you need to start getting your production apparatus up and running, and you need to get other external people into the process in order to make things happen. So the incurred cost, the money that you actually pay, they are not so much in the beginning, but they run very quickly at the end. But this is not the point of this exercise that we have here. The point of the exercise is actually a second curve that you can see here. And the idea is that when you get to the last part of the curve, you already, of the incurred cost curve, the first one that I drew, you already know what your product looks like because you have designed everything. So you know which materials it's made of, you know which manufacturing processes it involves, and so on. So you can't really do much. You have to pay up and have to pay the money that is necessary to make things happen. So the idea is that at the beginning of the process, when the engineers were throwing the ideas around, possibly without knowing it, they were making some very expensive decisions because they were deciding on all of the concepts that would later determine the cost of the product. So the committed cost runs very quickly in the beginning and not so fast at the end. And all of this is an argument why you should emphasize the importance of the conceptual design. So if you don't get the conceptual design right, then you will end up paying a lot of money that you might have otherwise saved. And that's the key point of this slide here. Okay, so that means that we're going to focus on the conceptual design of our exoskeleton because we don't want to commit too much cost. So this is the focus of the presentation here in the beginning of the design cycle. So the first thing we're going to do is we're going to come up with a load analysis. And for this purpose, we need two different musculoskeletal models. We need the actual working task, which is the one that you see over here on the right-hand side. This is the person lifting the box and taking a little step and then placing the box on a high shelf. And so this is a model that has been developed by conducting a simple experiment using an X-Sense system. It actually takes only, maybe 20 minutes or half an hour to do this. You don the X-Sense suit and you do the motion, and then you take the data out and put them into anybody. This is much easier than it used to be, and you can do this in situ. I mean, you can do this in the actual workplace. You don't have to get people into the lab and so on in order to make the experiments. So this is actually quite easy now. The other model that we're using is what we call a baseline model, and this is the gait model that you see here over here on the left-hand side. And the baseline model we use to have numbers to compare with. So the working task model is going to tell us what the loads are on the body in different parts of the body and in different sequences of the motion. And these are all numbers. And in order to figure out whether the numbers are too big or too small or whatever, we need something to compare them with. And we're using the gait line, the baseline model for that, because we know that gait is something that you can do for a very long time and with a lot of steps every day without without being injured by that. Okay, so that's what we're going to do. And let me show you an example of this. So if we look at the knee compression forces from the gait model, you can see that on the left-hand side, and you should focus on the low forces here. On the negative forces here. So these are the compressions in the knee, and you see this is about 2,500 newtons. So that would be 2.5 or 3 times body weight, depending on how heavy the subject is. And then if we look at the same thing in the lifting task, you can see on the right-hand side we have a blue and a yellow orange curve. They are not exactly the same because those are for the right and left leg, and the 2 legs are not doing exactly the same here. But you can see that the forces are on the same level, so they're about 3,000 Newton here. They're a little bit bigger than they were before because we're lifting the box, but not so much actually. So these are similar. This means that I wouldn't be that concerned about the forces in the knee, or should I say the compression forces between the femur and the tibia for this case. However, if we look at a different knee force, if we look at the forces between the patella and the femur, then that's a different story. This is the force that is generated because of the pull of the quadriceps on the patella on one side, and the pull of the patella ligament on the patella on the other side. And for gaits, we get a picture like this over here on the left-hand side. Again, you should focus on the negative numbers. It's the orange curve here that is the interesting one, because this is the compression of the patella against the femur. And you can see that we go to a value here of about maybe 250 Newton negative for the gait cycle. And over here in the lifting task, you can see that in the beginning, where we flex the knees a little bit to lift the box, you can see that the forces are actually much higher here. They're more than 750. So this is a factor of 3 in difference between gait and the actual working task. And of course, we would also be interested in the lumbar spine compression, because we're lifting something and we're stooping over and bending our backs. So there's a high probability that the back would be highly loaded here. And that's also what we see if we look at the back loads. And here you should focus on the positive numbers. Sorry about that. But if you look at the back loads in gait, you can see that we go up to around 800 Newton for this model. But if you look at the actual lifting task, you can see that we go up to 3,000 Newton in compression. In this case, it's between L5 and the sacrum. But it's quite similar for the other lumbar vertebrae as well. So you can see in this case, it's a factor of 4 higher for the lifting task than it is for normal gait. So this would probably also be a place to beware of whether there could be injuries forming in the body if you were to do this working task all day for a long life. Then this would be a point of focus, I would say. Of course, we could look at all sorts of other forces in the body. There would literally be tens of thousands of numbers that you could check out in the model in difference between gait and the lifting task. But we'll just, for the sake of the argument here, we'll just take these 2 and we'll just focus on them. So this was a load analysis. Now we have identified 2 loads that we want to unload by building an exoskeleton. And so we go to the conceptual design. And we have to start generating ideas for how we can design the exoskeleton using the output of the analysis. And here comes the part that might be tricky for those of you who have not used anybody before. So I'm going to offer a little bit of explanation for what we're going to do now. And I want you to imagine a joint. It could be a joint anywhere in the body. Could be a joint in the between 2 bones in the finger, like the ones that are shown here. And then imagine what the joint is doing, mechanically speaking. So the joint is holding the 2 bones together. So that means that the joint is making sure that when the bones are moving, they don't come apart. They are actually kept together. So So the joint works like a kinematic constraint. So it influences the kinematics of the model. But it's also a force provider, because in order to keep those two bones together, the joint has to provide reaction forces so that the two bones don't come apart, regardless of what external forces are working on them. And this is the way it is in reality. Joints would provide motions, and they would also provide, or they would provide kinematics, and they would also provide reaction forces. But in a mathematical simulation system like anybody, we have the luxury of being able to do other things as well. We can actually separate kinematics from kinetics in a system like that. So if you think of something which is purely kinematic and not kinetic at all, you can think about the optical markers that would drive a model if we had done an optical motion capture experiment. In that case, we would have marker trajectories for a lot of different points on the body, and we would want those markers to kind of grab the body and move the body through whatever motion has been measured in the lab. However, we wouldn't want those markers to provide forces to the body, because in reality, they didn't do that. In reality, when we did the experiment, it was the body that was driving the markers and not the other way around. So we would want this information to be purely kinematic. So there shouldn't be any forces involved between the markers and the body. And so that way we can specify drivers that are purely kinematic. We can also do the opposite. So we can also do something which is purely kinetic. And I can't really draw a picture of that, but I'm going to show you in a moment how it's done. We can define something which is called an any react force. So that's an object that you could define in anybody. And the best way to think about it is that the any react force is like an ideal motor that I can attach anywhere I want on the body. It is weightless, it doesn't have any mass, it doesn't consume any energy, and it is infinitely strong if I wanted to, but it's also perfectly controlled in such a way that at any point in time, at any given posture, this any react force, this wonderful motor, will provide exactly the amount of force which is necessary to support the body as well as possible in the position where I added this reaction force. Okay, it might be a little bit hard to understand, but I think you will understand it in a moment when I show you how it works. So just think of it like a wonderful motor that we can add, which is perfectly controlled and has no limitations in terms of forces or energy or anything like that. It's completely unrealistic, but it's going to be a nice design tool for us now. Okay, so these two latter elements I showed you here, the purely kinematic and the purely kinetic, those are mechanical abstractions that we can make in a computer system, but we can't make them in reality. So what we're going to do is we are going to look at the first idea that we might get. And this first idea we'll get from the load analysis. So the load analysis showed us that there was about 3 times as much load on the patellofemoral joints when we were doing our lifting task as there was if we were just walking. And so it might be a good idea to do something about that. And the something that we're going to do about it is that we can think about an exoskeleton which would extend the knee. So we would add an exoskeleton to the knee, and the role of this exoskeleton would be to perform knee extension. Now, why would that be a good idea? Well, it would be a good idea because knee extension is normally done by the quadriceps muscle in the thigh. And this quadriceps muscle is the one that is pulling on the patella. And that is the reason why we get these high patella forces, patellofemoral forces that I talked about initially. So it means that if we can offload the quadriceps muscle, then we will also very likely offload the patellofemoral forces. So what I do is I add my wonderful motor to the knee joint. And for those of you who have insight in how anybody works, you will be able to recognize some of this. So this is a screenshot of anybody you have over here on the right-hand side. And inside the model, which is programmed in this programming language, AnyScript, I will add these 1, 2, 3, 4, 5 lines of code. And this is actually all it takes. You can see the lines of code magnified over here on the left-hand side. So I'm defining an any react force, and inside the any react force, I'm simply pointing to the two knees, the left knee and the right knee. And this means that now there will be a perfectly controlled motor that will help doing the knee extension. And then I can do the analysis again, exactly the same motion as I had before, exactly the same loads, except that now I have an idealized motor that comes from an exoskeleton that might be in our future, which we have added to the model. And so what do we get? If we look at the left-hand graphs here, you can see the original forces between the patella and the femur. Again, it's the orange curve that we have here. Goes down to about 750 Newton. And if you look over on the right-hand side, you can see what we get when we add our wonderful motors. And of course, it reduces the patellofemoral forces a lot, just like I expected. Because remember, like I said, this was a perfect, almost God-made exoskeleton, much better than anything we could possibly hope to make in reality. Okay, so where did this bring us? It just told us that it might be nice to add some knee extension. Well, it actually does much more than that, because I can now go and investigate what my wonderful motor is doing. And I'll do that on the next slide here. So on this slide, I have taken all of the, for all of the time steps, I have taken the knee angle of the right and left leg, respectively. And then I have also taken the size of this reaction moment, which remember is optimal for the case. So the system has computed what the size of the reaction moment is. And then I get all of these blue dots here. And all of these blue dots, they show different combinations of knee angles and reaction moments that have happened in the knee after or this knee motor that I added to the problem. And you can see that they're kind of chaotic, but you can also see that they are not uncorrelated. There's actually a nice correlation. And I can add a trend line to this graph. And then I get the dotted line here in the middle. And I can even get Excel to write out the equation for me. And the equation says that the force, in this case, which is y, should be equal to minus 89 times x minus some constant. And when you have a combination of a force, or in this case a moment, which is proportional to a displacement, which in this case is an angle, then of course you recognize that what we have here is a linear spring. And now suddenly we have something that is quite easy to make. It does not require any motors, it does not require any control systems. It simply requires us to define a torsional spring and add it to an exoskeleton that crosses the knee. And then the torsional spring should have the spring characteristics that you see right here on the screen. So what we do now is we replace the reaction moments that we had before, our wonderful motors, we replace them with something much more benign, which is simply a spring in each leg. So a spring that is a torsional spring crosses the knee joint. And we add our identified properties of the spring constant and the slack length. In this case, the slack length here is the offset that you have at the end of the spring force. And then we add them, and then we run the analysis again after, of course, we remove our idealized motor. So now we just have the springs. And we run the analysis again. Again, here on the left-hand side, you see what we have if we have no exoskeleton. And on the right-hand side, you see what we get when we have the exoskeleton. And just as I expected, the forces will be gone completely from this initial part of the motion where the forces were high before. And then there's a little bit left over here in the later part of the motion. And you might ask, why would that be now that we have an almost idealized exoskeleton to carry the weight? And the reason is that the quadriceps has one head that also crosses the hip joints, and this would be the rectus femoris head. And this head of the muscle also has to do work when the hip needs flexing. and so there will be a little bit of force on the kneecap remaining because of that action. And this is a little bit that is left here in the graph on the right. So this is actually the principle that we're going to use to design exoskeletons. We have only done it for the knee so far, and as you remember, there was also a problem with the spine, and the problem with the spine was even bigger than it was for the knee. So we could go ahead and we could do exactly the same for the spine. We could design an exoskeleton that would go somewhere from the thorax to the pelvis, maybe down to the thighs or something like that, and which would be some sort of spring that would help us extend the spine. But we could also do something else. We could also say, okay, let's try to figure out something which crosses the spine as well as the knees at the same time. And then maybe we can do something good with only one component and not with two different exoskeletons. So not an exoskeleton for the upper body and one for the lower body, but one exoskeleton that would do the whole job at the same time. And the idea that we can come up with is the one that you see here. So here I have added these two red lines that you see in the picture. These are two extension rods. So you can think of them as linear springs that have been embedded inside some sort of cylinder piston arrangement, so that you can compress these lines, and the lines will perform a distraction force between the lower leg and the thorax. But I'm going to do it exactly the same again because I don't know which properties these springs should have. So what I do is I simply add an any react force to each of these two extensible rods, and then I run the analysis once again, and then I get the following. Then I get this, and it looks exactly like the for the patellofemoral force. It looks exactly like the picture you had before, because once again now I have made an idealized exoskeleton that will offload the body as much as possible, but now only using the extension rod. If we look at what happens with the spine, then the original spine force was the one we have here on the left-hand side. This is the one that we have if we have no exoskeleton. And the one we get if we have the extension rods and we have these idealized motors built into the extension rod, then we get what you see on the right-hand side. So you see the forces dropping almost pretty much to zero in the beginning of the motion, and a little bit later they're a little bit larger than zero, but they're still rather small compared to what we had before. Okay, so the question now is, can we do this using springs? And so I will do exactly the same exercise that I did before. I will investigate what the forces in the extension rods are if I have an idealized motor built into them. And that's what you see on this graph here. You can see here we have the rod length, and here we have the force in the rod. And you can see here that this is an ideal an ideal spring that will give you more force when the rod is compressed and less force when the rod is extended. Except at the very end, you see there's a climb in the curve here at the end of the motion. So if we divide this up, we can say that we can approximate the first part of the curve here. We can approximate that very well because it's almost linear. We can approximate that very well using a spring. The last part of the curve we cannot approximate using a spring, but I'm actually not very concerned about that because the last part of the curve here is when the person is standing up, and we didn't have very high forces in the spine after the spine extension was completed. It was mostly when the spine was flexed that we had the large forces. So I don't really care that I need a lot of force in order to do well at the end, because I'm mostly interested actually in the beginning of the motion. So I'm just going to go ahead and I'm going to approximate this with a line. It turns out that the slope here is about 1000 Newton per meter. So that would now be the spring constant of the springs that I would have to build into my extension rods. And I'm just going to do that. I get a slack length of the extension rod about 1.35 meters. I can read that from this curve as well. And then I go ahead, I build it in, and yes, we get something which looks very nice for the patellofemoral forces. This is the original here on the left-hand side again. Remember, minus 750. And on the right-hand side, you see we get much less. We get almost nothing in the beginning, and we get minus 250 a little bit later. But this is only a third of what we had before, and for gait it was about 300 Newton. So this is not so bad. It looks like it works well for the patellofemoral force. And if we go to the spine, we see the same pattern with the spring. We see that the originally very large compression force in the spine of about 3000 Newton has now been reduced down to about 1000 Newton, which is exactly in the beginning when we grab the box. And then this goes down, and then it comes up again to about 1000 Newton when we place the box on the shelf. So this is not with the idealized motor anymore. This is with the spring. So you see, even though we discarded the need for a high force at the end, this didn't make much of a difference anyway, because the forces were not so high at the end of the curve anyway. You see we have reduced slightly here at the end of the curve, but the forces were not so high anyway from in the beginning either. So it looks like this will actually work quite well. And this brings us to the end of it. So now we have made a conceptual design of the exoskeleton. You can see the motion here in the animation. You can see how the model is moving with the rods on. We can also check whether the rods are going to be in the way of the arms or other things when you're doing this working process. It doesn't seem to be very bad, but of course the detailed design could make this better. You could these rods wouldn't have to be straight; they could be curved. They could follow the body in more interesting ways, and you could probably improve it further with detailed design here. But the conclusions I want to convey to you is that it is possible to do simulation-based conceptual design if you use the right tools. Then you can actually get ideas just from doing the analysis, the musculoskeletal analysis, and looking at the results. You can figure out which elements are necessary in the exoskeleton in order to relieve the load on the body. And then you can do a conceptual design. The use of this any react force is really crucial because that is what every time leads us to the idea on how we can design the conceptual exoskeleton. And you can go along with a few iterations in this process. Yeah, so with that, I think that was all. Thank you very much for your attention, and I give the word back now to Christopher.
Thank you very much, John, for an interesting presentation. And just before we go to the question and answer session, I would like to say a few words about our online resources and also our upcoming events. So I'll just make myself the presenter once again. So if you want to know more about Anybody Technology, then you can go and check out our website at anybodytech.com, where you can find different events, special dates, and also all of the previous webcasts. It is also here we have a full publication list of studies using the Anybody modeling system. So if you want to check out what has been done in your field before, you can go and have a look there and get some inspiration. You can also check out our website anyscript.org, which is our community website for people using Anybody. And here you will find multiple online resources as our wiki page, several blog posts, and also links to our repository sites. It's also here our forum is located, and you can go and ask questions and get help from some fellow Anybody users. Then I would also like to announce our presence during the Veracon event in Scottsdale, Arizona on April 25th to 26th. And Anybody Technology will be represented there. So if any of you are attending and you want to meet up with us, then please reach out to me and let us arrange a meeting or just a short cup of coffee. And last but not least, if you have any questions or you want to meet up with us, or in case you are interested in a trial version of our software, then please feel free to send us an email at sales@anybodytech.com. And if you have any follow-up questions regarding this webcast or any of the previous ones, then please feel free to send me an email at kai@anybodytech.com or reach out to me through LinkedIn. And I think this brings us to the Q&A session, but just before we take the first question, I just want to thank you for the attention so far.